Hello and welcome to Neptune Files. Tonight we're going somewhere no human being has ever gone, somewhere no human being could ever go and return to tell about it. We're going to fall into a black hole, not quickly, not carelessly. We're going to do it slowly, deliberately, moment by moment, describing everything we see, everything we feel, everything that happens to the fabric of space and time around us as we descend into the most extreme object in the known universe. A place where gravity becomes so intense that it bends light, stretches time, warps space, and ultimately tears apart everything, every atom, every particle, every concept of distance and direction that dares to cross its threshold. This is a journey with no return. Once we cross a certain invisible boundary in space, there will be no coming back. No engine, no force, no amount of energy in the entire universe will be enough to carry us out again. We will fall, and we will keep falling until we reach a place that our best theories of physics cannot describe. A place where density becomes infinite, where curvature becomes infinite, where the equations that have governed our understanding of reality for more than a century simply break down and return nonsense. That place is called the singularity, and it is waiting for us at the center of every black hole in the universe. But we're not there yet. We're not even close. Right now, we're far away, drifting in our spacecraft, safe and comfortable, looking out the window at the stars, and somewhere ahead of us in the direction we're traveling, there is a region of space that looks slightly wrong. The stars in that part of the sky seem to wobble. They seem to shift and dance, as though seen through a heat haze on a summer highway, except there is no heat, no air, no highway. There is only the vacuum of space and the invisible hand of gravity reaching out across millions of kilometers, gently bending the light from distant stars as it passes near something massive, something dark. Something that emits no light of its own. We are approaching a black hole, and tonight we're going all the way in. So settle in, let your breathing slow, let the room around you fade into the background, and let's begin the longest fall imaginable. Let's start by understanding what we're falling into. A black hole is not a hole, it's not a gap in space. It's not a tunnel or a portal or an absence. A black hole is an object, a real physical object with mass and spin, and in some cases, electric charge. It is what remains when a massive star dies and its core collapses under the force of its own gravity, compressing all of its mass into a region so small, so dense, that the gravitational pull at its surface exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing that enters this region can ever escape. Not matter, not energy. Not light, not information, nothing. The boundary of this region is called the event horizon. It's not a physical surface. You can't touch it, stand on it, or bounce off it. It's a mathematical boundary, a sphere in space that marks the point of no return. Outside the event horizon, escape is possible. Inside, it is not. The event horizon is the edge of the knowable universe, a one-way membrane through which things can fall in but never come out. And it is, in a very real sense, the border between our universe and something else entirely. Something we cannot observe, cannot measure, and cannot fully understand. The black hole we're approaching tonight is a supermassive black hole. Not one of the small ones, the stellar mass black holes formed from the collapse of individual stars, which have masses of perhaps 5 to 50 times the mass of our Sun and event horizons, only a few dozen kilometers across. No, we're approaching something much larger, a black hole with a mass of about 10 million times the mass of the Sun. Its event horizon is roughly 60 million kilometers in diameter, about 40% of the distance from the Earth to the Sun. It is an object of almost incomprehensible scale, a gravitational monster that sits at the center of a distant galaxy, holding billions of stars in its orbit, shaping the structure and evolution of everything around it. We chose a supermassive black hole for a reason. If we tried to fall into a small, stellar mass black hole, the tidal forces near the event horizon would be so extreme that they would tear us apart long before we crossed the boundary. The gradient of gravity, the difference in gravitational pull between our feet and our head, would stretch us into a thin strand of atoms, a process colorfully known as spaghettification. We would be killed violently millions of kilometers from the event horizon, and we would never experience the crossing itself. But a supermassive black hole is different. Because the event horizon is so large, the curvature of space-time at the boundary is actually quite gentle. The tidal forces at the event horizon of a 10 million solar mass black hole are surprisingly mild, less than the tidal forces you experience on Earth from the Moon. You could cross the event horizon of a supermassive black hole and, for a time, feel nothing unusual at all. No jolt, no barrier, no wall of fire, just the continued gentle sensation of falling. This is one of the most counterintuitive things about black holes. The most dramatic boundary in the universe, the point of absolute no return, is completely undetectable to the person crossing it. So that's where we're going, a supermassive black hole, large enough that we can survive the crossing and experience what lies beyond, at least for a while. Eventually, even inside a supermassive black hole, the tidal forces will grow. They will become extreme and they will destroy us, but that comes later. For now, we are far away, and the black hole is just a subtle distortion in the starfield ahead, a shimmer, a wrongness in the sky, a hint of something massive hiding in the dark. Let's talk about what the black hole looks like from a distance. Because despite being called black, a black hole is not invisible, far from it. In fact, if the black hole is actively consuming matter, it can be one of the most luminous objects in the universe, blazing with the light of billions of suns. The light doesn't come from the black hole itself. Nothing escapes from within the event horizon. The light comes from the matter falling into the black hole, matter that has been captured from nearby stars, gas clouds, or other objects and drawn into a swirling disk of superheated material called an accretion disk. The accretion disk is one of the most violent environments in the universe. Matter spiraling toward the black hole is compressed and heated by friction and gravitational energy to temperatures of millions or even billions of degrees. At these temperatures, the matter radiates across the entire electromagnetic spectrum, from radio waves to visible light to X-rays and gamma rays. The energy output can be stupendous. An actively feeding supermassive black hole, known as a quasar or active galactic nucleus, can outshine its entire host galaxy, radiating the energy of trillions of suns from a region no larger than our solar system. But let's say our black hole is relatively quiet. It's not actively feeding on large quantities of matter. There's some gas and dust trickling in, forming a thin, faint accretion disk, but it's not the blazing inferno of a full quasar. This is actually more typical. Most supermassive black holes, including the one at the center of our own Milky Way, Sagittarius A star, are relatively quiescent. They have accretion disks, but faint ones, barely detectable even with our best instruments. From a distance of several light years, the black hole is invisible against the background of stars. It emits no light. Its accretion disk, if it has one, is too faint to see at this distance. The only hint that something is there is the subtle distortion of the starfield. Stars near the direction of the black hole appear to be in slightly wrong positions. Their light is being bent by the black hole's gravity, a phenomenon called gravitational lensing. As light from a distant star passes near the black hole, the curvature of space-time deflects the light's path, causing the star to appear shifted from its true position. Stars directly behind the black hole have their light bent around it, sometimes forming a complete ring of light called an Einstein ring, named after Albert Einstein, whose general theory of relativity predicted this effect more than a century ago. As we move closer, the distortion becomes more pronounced. Stars near the black hole's position seem to crowd together, as though being pushed aside by an invisible sphere. The sky behind the black hole becomes increasingly warped. Stars that should be hidden behind the black hole are visible, their light bent around it, creating a halo of displaced starlight. The effect is mesmerizing. It's as though space itself is a sheet of glass, and someone has placed a heavy ball on it, causing everything behind it to bulge and stretch and wrap around the edges. At a distance of about 1 light year, roughly 10 trillion kilometers, the gravitational influence of the black hole is noticeable but gentle. We are well within its sphere of influence, the region where its gravity dominates over the gravity of other nearby objects. If there were stars orbiting the black hole at this distance, they would take thousands of years to complete a single orbit, moving at speeds of a few hundred kilometers per second. We, in our spacecraft, are falling inward, accelerating slowly, drawn by a gravitational pull that will grow stronger with every kilometer we travel. Let's pause here for a moment. Let your mind settle into the image. You are in a spacecraft falling toward an object that contains 10 million times the mass of the Sun, compressed into a sphere 60 million kilometers across. The stars around you are distorted, bent, shifted by the curvature of space-time. Ahead of you, the sky is warped into an increasingly bizarre pattern. Behind you, the stars of the distant universe still look normal, familiar, comforting. But ahead, something is wrong. Something is pulling at the fabric of reality itself, and you are falling toward it. Let's continue. As we move closer, covering the distance over weeks and months in our spacecraft, the visual effects become more dramatic. At a distance of a few billion kilometers, roughly the scale of our solar system, the black hole's gravitational lensing creates a stunning optical phenomenon. The black hole itself appears as a perfectly circular region of darkness, the shadow surrounded by a thin, bright ring of light. This ring is not the accretion disk, at least not directly. It is the photon ring, a halo of light created by photons that have been captured into unstable orbits around the black hole, circling it one or more times before escaping toward our eyes. The photon ring marks the boundary of the photon sphere, a region at 1.5 times the radius of the event horizon, where light can theoretically orbit the black hole in a circle. No material object can orbit at this distance. The orbit is unstable, and any perturbation will send the object either spiraling into the black hole or flying away. But photons, traveling at the speed of light, can briefly orbit here, creating a brilliant ring of concentrated light that outlines the black hole's shadow against the sky. The shadow itself is larger than the event horizon. It appears about 2.5 times the radius of the event horizon, because light passing close to the black hole is deflected inward, creating a dark region larger than the physical boundary. This is what the Event Horizon Telescope captured in 2019, when it produced the first direct image of a black hole's shadow, the supermassive black hole at the center of galaxy M87, 55 million light-years away. That image, a bright ring of orange light surrounding a dark central void, was one of the most important astronomical images ever taken. And it showed us for the first time what a black hole actually looks like. Now imagine seeing that not in a processed radio telescope image, but with your own eyes. The ring of light is not orange. That color in the famous image was chosen for clarity. In reality, the accretion disk and photon ring emit light across a wide range of wavelengths. Some of it is visible light. Some is ultraviolet, some is X-ray. What you would actually see with your naked eyes depends on the temperature and composition of the accreting material, but it would likely appear as a brilliant white-blue ring of light, painfully bright near the inner edge and fading to dimmer, redder hues at the outer edge, and at the center the shadow, darkness. Not the darkness of an unlit room, but the darkness of a region from which no light escapes, the darkest dark possible, the absence not just of light, but of the possibility of light. Around the shadow, the universe is a funhouse mirror. Stars that are actually behind the black hole appear as a ring of light around the shadow, their photons bent around the black hole by gravity. Stars to the sides are shifted and distorted, smeared into arcs. Multiple images of the same star appear at different points around the black hole, created by photons that have taken different paths through the curved space-time. Some passing above the black hole, some below, some spiraling partway around before escaping. The effect is like looking through a crystal ball, except the distortion follows the precise mathematical rules of general relativity, rules that Einstein worked out on paper in 1915, and that describe with extraordinary accuracy the behavior of space and time in the presence of mass and energy. There is something else you would notice as you approach. Something that isn't visual, it's temporal. Time itself is beginning to behave differently. Einstein's general theory of relativity tells us that gravity affects time. The stronger the gravitational field, the slower time passes. This is not a metaphor. It is not an analogy. It is a measured, verified, physical fact. Clocks in stronger gravitational fields tick more slowly than clocks in weaker fields. GPS satellites, which orbit the Earth at about 20,000 kilometers altitude, where gravity is slightly weaker than on the surface, run their clocks slightly faster than identical clocks on the ground. The difference is tiny, about 45 microseconds per day, but it's real. And if it weren't corrected for, the GPS system would accumulate errors of about 10 kilometers per day. Near a black hole, this effect is extreme. As you fall closer to the event horizon, time slows down relative to a distant observer. If someone far away were watching you through a powerful telescope, they would see your clocks ticking more and more slowly. Your movements would appear to slow down. Your radio transmissions would be stretched to lower and lower frequencies, redshift by the gravitational time dilation. You would appear to be moving in slow motion, as though the universe were pressing the brakes on your personal timeline. But here's the crucial thing. You wouldn't notice any of this. To you, inside your spacecraft, time would feel perfectly normal. Your clocks would tick at their usual rate. Your heart would beat at its usual rhythm. You would eat, sleep, breathe, and think at the same pace as always. The slowing of time is only apparent to a distant observer. From your perspective, it's the rest of the universe that has changed. If you looked back at the distant stars, you would see them moving faster. Their light would be blue shifted, compressed to higher frequencies by the same time dilation that makes your time appear to slow from their perspective. Events in the outside universe would appear to speed up, as though someone were pressing fast forward on everything beyond the black hole's influence. This asymmetry is one of the most profound aspects of general relativity. There is no absolute time. There is no universal clock ticking at the same rate for everyone. Time is local. It depends on where you are and how strong the gravitational field is. Two observers in different gravitational environments will disagree about how much time has passed between two events, and they will both be right. There is no contradiction. Time itself is flexible, elastic, shaped by the presence of mass and energy, and near a black hole it is stretched to the breaking point. Let's continue falling. We are now at a distance of about 1 billion kilometers from the event horizon. This is roughly the distance from the Sun to Jupiter. The black hole's shadow dominates the sky ahead of us, a vast, perfect circle of darkness spanning a significant portion of our forward view. The photon ring blazes around it, and the distorted images of background stars create an ever-shifting kaleidoscope of light around the dark center. At this distance, the tidal forces are still negligible. We feel weightless, as we would in any freely falling reference frame. This is another key insight from general relativity, and it's worth pausing to appreciate. When you're in free fall, you don't feel gravity, you feel weightless. An astronaut in the International Space Station is in free fall, constantly falling toward the Earth, but moving sideways fast enough to keep missing it. And they feel weightless. A skydiver, before opening their parachute, feels weightless. And we, falling freely toward the black hole, feel weightless too. This is because gravity, in Einstein's framework, is not really a force at all. It's the curvature of space-time. Objects in freefall are following the straightest possible paths through curved space-time, paths called geodesics. They are not being pushed or pulled. They are simply moving along the natural contours of space and time, like a marble rolling along the surface of a curved bowl. The marble doesn't feel any force. It just follows the shape of the bowl, and we, falling toward the black hole, are just following the shape of space-time. We feel nothing. What we would feel eventually is tidal forces. These arise not from gravity itself, but from the difference in gravity between two nearby points. If your feet are closer to the black hole than your head, your feet experience a slightly stronger gravitational pull, and this difference stretches you along the direction of fall. At the same time, the curvature of space-time compresses you from the sides, squeezing you laterally. The net effect is a stretching along the direction of fall and a squeezing perpendicular to it. This is the tidal force, and it's what will eventually destroy us. But for now, at 1 billion kilometers out, the tidal forces are imperceptible. We feel nothing but the gentle sensation of floating, of weightlessness, as we fall deeper into the gravitational well of the black hole. Let's talk about the accretion disk. If our black hole has one, and most do to some degree, it would be visible as a vast, flat, glowing structure surrounding the black hole. The accretion disk is not a simple ring like Saturn's rings. It's a complex dynamic structure with a definite inner edge called the innermost stable circular orbit, or ISCO. Inside this radius, no stable orbit exists. Any matter that crosses the ISCO will spiral rapidly into the black hole within a few orbits. The ISCO is at 3 times the radius of the event horizon for a non-spinning black hole and can be much closer for a rapidly spinning one. The disk itself is thin relative to its diameter, but it can extend for millions of kilometers. The inner regions are extraordinarily hot, glowing with the white-blue light of gas heated to millions of degrees. The outer regions are cooler, radiating in the infrared and radio parts of the spectrum, appearing as a dimmer, redder glow. The temperature gradient creates a spectrum of colors, from the brilliant blue-white of the inner edge to the deep red of the outer regions. Though much of the radiation is invisible to the naked eye, lying in the ultraviolet and X-ray bands. But the accretion disk doesn't look like a flat ring when seen from nearby. Gravitational lensing warps its appearance in bizarre ways. Imagine the disk as a flat plane surrounding the black hole like the rings of Saturn. Now imagine looking at it from slightly above the plane. You would expect to see the near side of the disk curving toward you and the far side curving away, with the black hole's shadow in the center. But that's not what you'd see. The light from the far side of the disk which should be hidden behind the black hole, is bent by gravity up and over the black hole, creating a luminous arch that appears above the shadow. Similarly, light from the underside of the disk is bent upward, appearing as a second arch below the shadow. The result is that you see the accretion disk wrapped around the black hole in a bizarre warped halo, a shimmering crown of light that defies your intuitions about geometry. This is exactly what was depicted, with remarkable scientific accuracy, in the 2014 film Interstellar, which worked with physicist Kip Thorne to simulate the appearance of a black hole with an accretion disk. The image was so accurate that it led to the publication of scientific papers about the visual properties of accretion disks near black holes. It was a rare case of Hollywood getting the science not just approximately right, but precisely right, producing images that are now used in astrophysics classrooms around the world. As we fall closer, the accretion disk fills more and more of our view. The inner edge blazes with light so intense that it would be painful to look at directly. The gas here is spiraling inward at a significant fraction of the speed of light, heated to tens of millions of degrees, radiating a torrent of X-rays and ultraviolet light. If we could see X-rays, the inner disk would be the brightest thing in our visual field, outshining everything else by orders of magnitude. In visible light, it's still extraordinarily bright. A seething, turbulent river of incandescent gas, swirling around the black hole in a flattened vortex. The gas in the accretion disk doesn't fall straight in. Conservation of angular momentum keeps it spiraling, orbiting the black hole many times before gradually losing energy through friction and radiation, and spiraling inward. The friction is generated by turbulent interactions within the disk, driven by magnetic fields that thread through the gas and create a kind of viscosity. This magnetically driven turbulence, known as the magnetorotational instability, is the engine that drives accretion, converting gravitational energy into heat and radiation with remarkable efficiency. Up to about 40% of the rest mass energy of infalling matter can be converted to radiation in an accretion disk around a spinning black hole, making it the most efficient energy source known, far more efficient than nuclear fusion, which converts only about 0.7% of rest mass energy. Some black holes also produce jets, narrow, highly collimated beams of plasma launched from the poles of the accretion disk at speeds close to the speed of light. These jets can extend for thousands or even millions of light years, carrying enormous amounts of energy far out into intergalactic space. The exact mechanism that produces jets is still not fully understood, but it involves the interaction of the spinning black hole's gravity with the magnetic fields of the accretion disk, twisting and focusing the fields into a tight beam that accelerates charged particles to relativistic speeds. If our black hole has jets, we would see them as two thin, brilliant beams of light extending from the poles, perpendicular to the accretion disk, stretching out into space like cosmic searchlights. But let's focus on our descent. We are now at a distance of about 500 million kilometers from the event horizon, roughly the distance from the Sun to Jupiter. We're falling faster now, our velocity climbing as we convert gravitational potential energy into kinetic energy. The black hole's shadow covers a significant portion of the sky ahead. The photon ring is a brilliant circle of light, and the warped accretion disk creates an otherworldly halo around the darkness. Something else is happening now that's worth noting. The light from the stars behind us, the stars in the direction we came from, is becoming increasingly concentrated into a smaller region of the sky. This is an effect called relativistic aberration. As we move faster and faster toward the black hole, the light from the universe behind us is compressed into a shrinking circle at our back, while the sky ahead seems to expand. It's a relativistic version of a familiar effect. When you drive in rain, the raindrops seem to come more from the front of the car, even if they're falling straight down. Similarly, as we move at increasing speeds, the light from all directions seems to shift forward, concentrating ahead of us. But since the black hole is ahead of us, and the black hole absorbs all light that enters its event horizon, the forward sky is dominated by the black hole's shadow, while the light from the rest of the universe is compressed into an increasingly narrow ring around the shadow's edge. The effect is eerie. The familiar stars of the cosmos, the comforting constellations, the reassuring background of distant galaxies, are being squeezed into a narrowing halo of light surrounding the abyss. It's as though the universe itself is being pushed to the margins, retreating from the advancing darkness. And in a sense, it is. The closer we get to the black hole, the more the black hole dominates our reality, our geometry, our physics. The outside universe becomes a shrinking window, a narrowing aperture through which we can still see the cosmos we left behind. Eventually, that window will close. Let's keep falling 200 million kilometers from the event horizon. The tidal forces are still manageable. A sensitive instrument could detect them, but a human body would not yet feel anything unusual. The gravitational time dilation is becoming significant. If we were to fire a laser pulse back toward a distant observer, they would measure its wavelength as being stretched, redshifted, the photons losing energy as they climb out of the gravitational well. The deeper we fall, the more redshifted our signals become, the more stretched our time appears to the outside world. From the perspective of a distant observer watching us through a telescope, something strange is happening. Our descent is slowing down, not because we're actually slowing down, we're accelerating, but because the time dilation is stretching out the intervals between the photons we emit. Our image is becoming dimmer and redder, our movements increasingly sluggish. If the distant observer could somehow watch us all the way to the event horizon, they would see us slow down asymptotically, never quite reaching the boundary, our image fading and reddening until it becomes indistinguishable from the black of the event horizon itself. From the outside, it would appear as though we freeze at the edge, embedded in time, never quite falling in. But this is an illusion created by the finite speed of light and the extreme time dilation near the event horizon. We do fall in, we cross the event horizon. We just can't send that information back to the outside universe, because the photons we emit after crossing the horizon are trapped, falling inward with us, unable to escape. The last photon we emit before crossing the horizon will take an extraordinarily long time to reach the distant observer, arriving redshifted to near invisibility and delayed by enormous amounts of time. But we, in our own reference frame, cross the horizon in finite time. No delay, no freezing, no drama, just the continued sensation of falling. Let's pause here for a moment. Take a slow breath. Feel the stillness of the room around you. We're getting close now, close to one of the most remarkable boundaries in all of physics, the event horizon. Let's make sure we understand what it is and what it isn't before we cross it. The event horizon is not a physical surface. There is no wall, no membrane, no barrier. If you were falling through it, there would be no flash of light, no moment of transition, no sign that says you are now inside the black hole. The event horizon is a boundary defined by the global structure of space-time, a property of the entire geometry of the universe, not something you can detect locally. It's like the point of no return in a river flowing toward a waterfall. Somewhere upstream, there's a point where the current becomes too strong to swim against. If you're in a boat drifting with the current, you pass that point without noticing. The water looks the same. The current feels the same. But you've crossed a threshold and now you're going over the falls whether you want to or not. The event horizon works the same way. Inside the horizon, space-time is curved so steeply that all paths, including the paths of light, lead inward. You can't turn around and go back, not because some force is preventing you, but because back no longer exists as a direction. The singularity is no longer in a particular direction in space, it's in the future. And just as you can't avoid moving into the future in normal space-time, you can't avoid moving toward the singularity inside a black hole. The geometry of space-time itself has been warped so profoundly that spatial and temporal dimensions have, in a sense, swapped roles. The direction toward the singularity becomes the future. The direction away from it becomes the past, and you can no more move away from the singularity than you can move backward in time. This is perhaps the most alien and disturbing aspect of the interior of a black hole. It's not just that gravity is strong. It's that the very structure of space and time has been fundamentally altered. The concepts of closer and farther lose their meaning. The concept of distance itself becomes ambiguous. Inside the event horizon, everything is falling. Space itself is falling, dragged inward by the extreme curvature, carrying everything with it, light included, toward the singularity. But let's not get ahead of ourselves. We haven't crossed the horizon yet. We're close, 100 million kilometers away. The shadow of the black hole now fills most of the sky ahead. The photon ring is a blazing circle of light, and beyond it, the compressed, distorted images of the entire universe are squeezed into a shrinking halo. Behind us, the universe we left behind is a diminishing circle of blue shifted light, the stars appearing brighter and bluer as their light is compressed by our increasing velocity and the gravitational blue shift of light falling into the well. At 50 million kilometers, we are approaching the event horizon. This is roughly 1/3 of the distance from the Earth to the Sun. The event horizon of our 10 million solar mass black hole has a radius of about 30 million kilometers, so we are within one event horizon radius of the boundary. The curvature of space-time is now extreme, though the tidal forces are still surprisingly mild because the event horizon is so large. If this were a stellar mass black hole, with an event horizon only a few kilometers across, the tidal forces would have torn us apart long ago. But the gentleness of the tidal forces near a supermassive black hole's event horizon is one of nature's strange mercies. It allows us, at least in principle, to experience the crossing. The light from the accretion disk is now coming from bizarre directions. Some of it is coming from below us, some from above, some from directions that seem impossible given the physical location of the disk. This is because photons emitted by the disk at various points can take wildly different paths through the curved space-time before reaching our eyes. Some photons circle the black hole one or more times before reaching us. We are seeing the same accretion disk multiple times, layered images created by photons that have taken different routes through space-time. The visual effect is overwhelming. The sky is a maze of light and darkness, of shifted and duplicated images, of colors ranging from brilliant blue-white to deep red, all wrapped around the immense featureless blackness of the shadow. And now, something remarkable is happening to the universe behind us. The shrinking circle of light that represents the outside universe is becoming incredibly bright. All the light from all the stars in the entire cosmos, all the photons that happen to be traveling in our direction, are being focused and concentrated into an ever smaller ring of light. This is the ultimate gravitational lens. The black hole is bending the light from the entire universe and concentrating it into a brilliant, intense point behind us. If we looked back, we would see the entire observable universe compressed into a glowing ring, blue shifted to enormous energies, all the stars and galaxies we've ever known, reduced to a circle of fire behind our head. It's a haunting image. The entire universe, everything we've known, reduced to a thin ring of light, growing smaller and brighter as we fall deeper. It's as though the cosmos is saying goodbye, concentrating all of its light into one final, brilliant farewell before we cross the threshold and leave it behind forever, 20 million kilometers from the event horizon. We are very close now. The tidal forces are becoming measurable, though still not painful. A sensitive accelerometer would detect a slight stretching along our direction of fall and a slight compression from the sides. Our spacecraft is beginning to feel these forces as subtle stresses in its hull, tiny creaks and groans as the metal is stretched by a few millionths of a percent. We don't feel it in our bodies, not yet. The time dilation is now enormous. For every second that passes on our clock, hours might be passing on a clock far from the black hole. If we could somehow send a message back to the distant universe, it would arrive enormously redshifted, the radio waves stretched to wavelengths of kilometers, carrying information at a glacial pace. And any message sent to us from the outside would arrive blue-shifted, compressed, carrying information at a frantic speed, as though the outside universe was speaking faster and faster, trying to cram all of eternity into the remaining moments before we cross the horizon. 10 million kilometers, 5 million, 2 million, 1 million. We are falling faster and faster, the velocity climbing toward a significant fraction of the speed of light. The event horizon looms ahead, not as a visible boundary, but as a mathematical threshold encoded in the geometry of space-time. We cannot see it. We cannot detect it. But it's there 500,000 kilometers. The shadow fills nearly the entire forward sky. A thin ring of impossibly bright, blue-shifted light, the compressed image of the entire universe, encircles the darkness. The accretion disk, warped and multiplied by gravitational lensing, blazes around us in a complex pattern of arcs and rings. We are inside the photon sphere now. Light emitted sideways from our position can orbit the black hole before escaping or being captured. If we shone a flashlight sideways, the beam would curve, following the curvature of space-time, bending toward the black hole. If we shone it backward, away from the black hole, the photons would still escape, but they would be enormously redshifted, losing energy as they climbed out of the gravitational well. If we shone a flashlight forward, toward the black hole, the photons would accelerate inward, blue shifting as they fell, gaining energy from the gravitational field. But it doesn't matter. Those photons are heading the same way we are, inward, toward the event horizon, toward the singularity, 100,000 kilometers. The event horizon is close, very close. In our own reference frame, we will cross it in minutes, perhaps less. The exact time depends on our velocity and trajectory, but it won't be long now. Let's take one last look back. Behind us, the entire observable universe is compressed into a small, brilliant circle of light. Every star, every galaxy, every photon from every source in the cosmos, focused by the black hole's gravity into a luminous point. It's beautiful. It's terrifying. It's the last view of the universe we will ever have. Because once we cross the event horizon, even if we look back, we will not see the universe as we knew it. The light from outside will continue to fall in after us, and we will continue to see it for a time, but it will be increasingly distorted, increasingly blue-shifted, increasingly concentrated, and eventually the tidal forces will make observation impossible. Here we go. We're crossing the event horizon now, and nothing happens. Let me say that again, because it's important. Nothing happens. There is no barrier, no flash, no sound, no sensation. The event horizon is not a place, it's a moment. It's the moment after which return becomes impossible, but the moment itself is indistinguishable from any other moment. The laws of physics don't change. The curvature of space-time doesn't suddenly jump. Everything is smooth, continuous, unremarkable. If you weren't doing the mathematics, If you weren't tracking your position with extraordinary precision, you would have no way of knowing that you had crossed the most profound boundary in the universe. This is one of the deepest insights of general relativity, and it's worth sitting with for a moment. The event horizon is a global property of space-time, not a local one. It's defined by what happens in the future, by whether or not outgoing light rays eventually escape to infinity. A local observer falling through the horizon cannot determine from local measurements alone that they have crossed it. The laws of physics in their immediate neighborhood look the same as they do anywhere else in curved space-time. The equivalence principle, one of the foundations of general relativity, guarantees this. A freely falling observer in a gravitational field is equivalent to an observer in empty space, at least locally, at least for a short time. And yet, something has changed. Something fundamental and irreversible. We are now inside the black hole and we can never get out. Let's think about what this means. Inside the event horizon, the singularity is not ahead of us in space. It's ahead of us in time. This is the crucial distinction. Outside the horizon, the singularity is a place, a location in space that you can choose to move toward or away from. Inside the horizon, it becomes a moment in the future, a time that you cannot avoid any more than you can avoid next Tuesday. No matter which direction you travel, no matter how hard you accelerate, no matter what you do, the singularity is in your future. It's not a wall that you're approaching, it's a deadline. The interior of the black hole is not a static chamber. It's a dynamic, evolving space-time, where the geometry is changing with time. The singularity is not sitting at the center, waiting for you. It's approaching from the future, closing in on all sides like the walls of a room that is slowly shrinking. Every moment that passes, the singularity is closer. Not closer in space, closer in time. You have a finite amount of proper time, time measured by your own clock, before you reach it. How much time? For our 10 million solar mass black hole, the answer is surprisingly generous. The proper time from the event horizon to the singularity for a freely falling observer is approximately proportional to the mass of the black hole. For our black hole, it works out to about 15 to 20 hours of proper time. That's right, hours. You could cross the event horizon of this black hole and live for nearly a day before reaching the singularity. You could eat a meal. You could sleep. You could have a long contemplative conversation about the nature of existence, all while falling inexorably toward the most extreme point in space-time. For a smaller black hole, the time would be much less. For a stellar mass black hole of 10 solar masses, the time from horizon to singularity is only about 1/10 of a millisecond. You would be destroyed almost instantly. But for our supermassive black hole, the interior is vast and the fall is long. So here we are, inside the event horizon, with hours of time remaining. What do we see? Looking back toward the direction we came from, we can still see the outside universe. Light from outside continues to fall through the event horizon and reach our eyes. The universe hasn't disappeared, but it looks different. The circle of light representing the outside universe is still there, but it's now above us, behind us, in the direction opposite to our fall. It's intensely bright and blue-shifted, the light from billions of years of cosmic history compressed into a concentrated beam, and something else. We can see light that crossed the event horizon after we did. Photons that were behind us when we crossed are now catching up, falling inward faster. We can see light from events that happened outside the black hole after we entered. In a sense, we can see the future of the outside universe, at least the near future, the events that occurred in the moments and minutes after we crossed the horizon. This light continues to reach us for a time, bringing news from a universe we can never return to. but we cannot send any messages back. Every photon we emit is falling inward, just as we are. Our light, our radio signals, everything we produce is trapped inside the event horizon, falling toward the singularity alongside us. We are cut off, completely, utterly, irrevocably cut off from the outside universe. We can receive, but we cannot send. We can see, but we cannot be seen. We are ghosts, falling through a one-way mirror, watching the universe recede behind us. As we fall deeper, the tidal forces begin to grow. Remember, the tidal forces near the event horizon were mild because the horizon is so large. But as we fall deeper into the interior, we're getting closer to the singularity, where the curvature of space-time becomes infinite. The tidal forces increase as we approach the singularity, slowly at first, then more rapidly. After a few hours of falling, the tidal forces become noticeable. We feel a gentle stretching along the direction of fall, as though invisible hands are pulling our head and feet in opposite directions. Simultaneously, we feel a compression from the sides, as though the walls of our spacecraft are closing in. The stretching and squeezing are the two components of the tidal force, the manifestation of the curvature of space-time in our immediate neighborhood. The stretching is strange and unsettling. It's not painful yet. It's more like the sensation of being on a medieval rack, but set to its gentlest setting. A persistent, steady pull, separating our head from our feet by an amount that is, for now, barely measurable, but it's growing. Every minute, the stretching increases. The force is proportional to our distance from the singularity, and as that distance decreases, the force grows without bound. Let's pause and breathe. Let the image settle. You are inside a black hole. The outside universe is a bright circle of light above you, growing smaller and bluer. The singularity is somewhere ahead of you, not in a direction you can point to, but in the future, approaching inevitably. And the tidal forces are beginning to make themselves known, a gentle but insistent reminder that this journey has an ending, and that the ending is absolute. As the hours pass, the tidal forces continue to grow. The stretching becomes uncomfortable, then painful. Our spacecraft is under increasing stress. The hull groans, seams begin to separate. Instruments register the differential forces. The difference in gravitational pull between one end of the ship and the other. This difference is what causes the stretching. It's the same force that causes tides on Earth. The difference in the Moon's gravitational pull between the near side and the far side of the planet, which creates the bulge of water that we call a tide. Near a black hole's singularity, the same effect, amplified to unimaginable extremes, will tear apart anything from a spacecraft to a planet to an atom. There's something worth understanding about why tidal forces grow as you approach the singularity, even though you're falling freely and feel weightless in the absence of tidal effects. The key is curvature. In general relativity, gravity is curvature of space-time. A freely falling object follows a geodesic, a straight line through curved space-time, and feels no force. But two nearby freely falling objects, following two slightly different geodesics, will find that their geodesics converge or diverge, because space-time is curved. This relative acceleration between nearby geodesics is the tidal force. It's a direct measure of the curvature of space-time, and near the singularity, the curvature becomes infinite. Let's keep falling. We've been inside the event horizon for several hours now. The tidal forces are growing stronger. Our bodies are being stretched along the direction of fall by forces that are now clearly noticeable, pulling our heads and feet apart with a persistent growing tension. The compression from the sides is also increasing, squeezing us laterally. The combination is deeply uncomfortable, a sensation unlike anything experienced in normal gravity. We are being reshaped by the geometry of space-time itself. At some point, the structural integrity of our bodies will be exceeded. The tidal forces will become strong enough to overcome the molecular bonds that hold our tissues together. This is the beginning of spaghettification, the process by which an object falling into a black hole is stretched into a long, thin strand of matter, like a piece of spaghetti being pulled from a ball of dough. The term spaghettification was coined by Stephen Hawking, one of the greatest theoretical physicists of the 20th century, who spent much of his career studying the properties of black holes. Hawking's work on black holes led to some of the most important insights in modern physics, including the discovery that black holes are not entirely black. They emit a faint radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation causes the black hole to slowly lose mass and, over unimaginably long timescales, eventually evaporate entirely. For a supermassive black hole like ours, the evaporation time is so long that it dwarfs the current age of the universe by a factor of a googol or more. But in principle, no black hole lasts forever. They are not eternal. They are born, they feed, they grow, and eventually, over timescales that make the age of the universe seem like the blink of an eye, they die. But we won't be around for that. We have much more immediate concerns. The tidal forces are now extreme. Our spacecraft has been torn apart, the hull ripped open by the differential gravitational forces. Pieces of debris stretch out above and below us, forming a long, thin column of material, all of it falling toward the singularity, all of it being stretched and compressed by the tidal forces. And now, the forces reach our body. The stretching overwhelms the strength of our bones, our muscles, our connective tissue. We are being pulled apart, slowly at first, then faster. Our body elongates, stretching in the direction of fall, thinning from the sides. The pain would be extraordinary, but mercifully brief, because the forces increase so rapidly that unconsciousness would follow almost immediately. Let's step outside the experience for a moment. Let's observe from a distance, from the safety of abstraction. What happens to matter as it approaches the singularity is a process of increasing tidal disruption. First, large structures are torn apart. A planet would be shredded into fragments. The fragments into boulders, the boulders into dust. Then molecular bonds are broken. Molecules are torn into atoms. Then atomic bonds are broken. Atoms are stripped of their electrons, ionized into a plasma of nuclei and free electrons. Then nuclear forces are overwhelmed. Nuclei are torn apart into individual protons and neutrons, and then, in the final moments, even protons and neutrons might be torn apart into their constituent quarks. What reaches the singularity, if anything can be said to reach it, is a stream of fundamental particles stretched to infinite thinness, compressed to infinite density, their identities and histories obliterated. This is spaghettification carried to its ultimate conclusion. The name is playful, almost whimsical, but the reality is absolute. Everything that falls into a black hole is destroyed, not just killed, destroyed, broken down into its most fundamental components, and then, at the singularity, those components themselves are subjected to conditions that our current theories cannot describe. The curvature of space-time becomes infinite, the density becomes infinite, the temperature and energy become infinite. Our equations break down. Our understanding fails. We have reached the edge of physics. The singularity is the great unknown at the center of every black hole. In the mathematical framework of general relativity, it is a point of infinite density and infinite curvature, a place where the equations produce infinities and cease to be meaningful. Most physicists believe that the singularity is not a real physical infinity, but rather a sign that general relativity is incomplete. that a more fundamental theory is needed to describe what happens when gravity becomes this extreme. That more fundamental theory is the long-sought theory of quantum gravity, a framework that would combine Einstein's general theory of relativity, which describes gravity and the large-scale structure of space-time, with quantum mechanics, which describes the behavior of matter and energy at the smaller scales. These two theories are the pillars of modern physics, and they are extraordinarily successful within their respective domains. But they are incompatible. They cannot both be correct in all situations. In particular, they give conflicting predictions in situations where gravity is extremely strong and distances are extremely small, precisely the conditions at the center of a black hole. Several approaches to quantum gravity are being actively pursued. String theory. One of the most prominent proposes that the fundamental constituents of reality are not point-like particles, but one-dimensional strings vibrating in a higher dimensional space-time. Loop quantum gravity, another approach, proposes that space-time itself has a discrete structure at the smallest scales, a kind of quantum foam made up of tiny loops of gravitational flux. Other approaches, including causal set theory, asymptotic safety, and various others, offer different perspectives on the problem. None of these approaches has been confirmed by experiment. The energies and distances involved are so extreme that testing these theories directly may be beyond our current or foreseeable technological capabilities. The Planck length, the scale at which quantum gravitational effects are expected to become important, is about 10 to the minus 35 meters, roughly 100 million trillion times smaller than a proton. No experiment we can imagine could probe distances this small, and the Planck energy, the energy at which quantum gravity effects become dominant, is about 1 billion times higher than the energies achieved by the Large Hadron Collider, the most powerful particle accelerator ever built. So the singularity remains a mystery. We do not know what happens there. We do not know whether the singularity is a true infinity, a region of incomprehensible density and curvature, or whether quantum effects smooth it out, replacing the singularity with something less extreme. Some theories suggest that the singularity might be a transition to another region of space-time, perhaps the birth of a new universe, a baby universe budding off from the parent through the black hole's interior. Others suggest that quantum effects create a minimum size, a Planck scale core of unimaginable density that replaces the infinite point of classical general relativity. Still others suggest that the interior of the black hole might connect through a wormhole or Einstein-Rosen bridge to another region of our own universe, or to a different universe entirely. These are speculative ideas, beautiful, mathematically sophisticated, but speculative. We have no way of testing them, at least not yet, and we may never be able to test them directly because the singularity is hidden behind the event horizon, forever inaccessible to external observation. Whatever happens at the singularity stays at the singularity. The cosmic censorship hypothesis, first proposed by Roger Penrose, suggests that nature always hides singularities behind event horizons, never allowing them to be seen from the outside. Whether this is always true is still an open question, but it seems to hold in all known physical scenarios. Roger Penrose won the Nobel Prize in Physics in 2020, along with Andrea Ghez and Reinhard Genzel, for his theoretical work showing that the formation of singularities is an inevitable consequence of general relativity under very general conditions. His singularity theorems, developed in the 1960s, proved that once a sufficient amount of matter is compressed into a small enough region, nothing can prevent the formation of a singularity. The collapse is inevitable, guaranteed by the mathematics of general relativity. This was a profound result, because it showed that singularities are not exotic anomalies or mathematical curiosities. They are a fundamental prediction of our best theory of gravity. And since black holes exist, and black holes contain singularities, the singularities exist too, whether we understand them or not. Let's return to our journey. Or rather, let's acknowledge that our journey is over. We have been stretched and torn and reduced to a stream of fundamental particles, falling toward a point of infinite density at the center of the black hole. We have experienced spaghettification. We have been destroyed. And whatever remains of us, whatever stream of quarks and leptons and photons continues to fall inward, will reach the singularity in a finite time as measured by its own rapidly diminishing clock. And then the story ends, or rather, the story enters a chapter that we cannot read, written in a language that we do not yet possess. But there is more to say about black holes. Much more, because the journey into a black hole is not just a physical journey. It's a conceptual journey, a journey to the edge of our understanding, a journey that reveals the deepest questions about the nature of reality. And those questions are worth exploring even here, even now, as we float in the imagined wreckage of our impossible expedition. Let's talk about the information paradox. This is arguably the deepest puzzle in theoretical physics, and it arises directly from the existence of black holes. Here's the paradox. In its simplest form, quantum mechanics says that information is never destroyed. Every physical process is, in principle, reversible. If you know the complete quantum state of a system at any moment, you can, in principle, calculate its state at any past or future moment. Information is conserved. This is a fundamental principle of quantum mechanics, as basic as the conservation of energy. But black holes seem to destroy information. When matter falls into a black hole, it crosses the event horizon and is lost to the outside universe. The information about what fell in, its composition, its structure, its quantum state, is trapped behind the horizon. And then, according to Hawking, the black hole slowly evaporates, radiating energy in the form of Hawking radiation. But Hawking radiation is thermal. It's random. It carries no information about what fell into the black hole. It's like the heat radiated by a warm object. It tells you the temperature, but not what the object is made of. So when the black hole evaporates completely, which it will, given enough time, the information about everything that fell in seems to have been destroyed. It's not inside the black hole, because the black hole no longer exists. It's not in the Hawking radiation, because the radiation is thermal and carries no information. The information has simply vanished, and that's a problem because quantum mechanics says information can never vanish. This is the black hole information paradox, first formulated by Hawking in 1976, and it has been one of the central puzzles of theoretical physics ever since. It pits two of the most fundamental theories in physics against each other. General relativity says that the event horizon is a point of no return, that anything crossing it is lost to the outside universe. Quantum mechanics says that information cannot be lost, period. Both theories are extraordinarily well tested and well confirmed, and yet they contradict each other at the event horizon of a black hole. Many resolutions have been proposed. One possibility is that the information is somehow encoded in the Hawking radiation in subtle quantum correlations between the emitted photons that are invisible to naive analysis but present in the full quantum state of the radiation. This would resolve the paradox, but the mechanism by which information escapes the black hole is far from clear. It would seem to require information to travel faster than light, or to tunnel through the event horizon, or to be transmitted by some non-local quantum process that we don't fully understand. Another possibility is that the information is stored in the final remnant of the black hole, a Planck-scale nugget of extreme density that remains after the evaporation is nearly complete. This remnant would carry all the information, but it would be extraordinarily small and would need to contain an enormous amount of information, leading to its own set of conceptual problems. Yet another possibility is that the interior of the black hole is connected to the Hawking radiation by quantum entanglement, creating a kind of wormhole between the interior and the exterior. This idea, developed by Juan Maldacena and Leonard Susskind, is captured in the equation ER equals EPR, which proposes that Einstein-Rosen bridges, which are wormholes, and Einstein-Podolsky-Rosen pairs, which are entangled quantum states, are fundamentally the same phenomenon. If this is correct, then the geometry of space-time itself is built from quantum entanglement, a breathtaking idea that connects the large-scale structure of the universe to the smaller-scale phenomena in quantum mechanics. The information paradox remains unsolved. It is one of the most important open problems in physics because its resolution will likely require a fundamental advance in our understanding of quantum gravity, the relationship between information and space-time, and the ultimate nature of reality. It's not just a puzzle about black holes, it's a puzzle about the foundations of physics itself. Let's talk about something else. Let's talk about what would happen if you fell into a different kind of black hole. The black hole we've been falling into is a Schwarzschild black hole, the simplest kind, defined only by its mass. It has no spin and no electric charge, but real black holes are almost certainly spinning. Stars spin, and when a star's core collapses to form a black hole, the spin is preserved and amplified, just as a figure skater spins faster when they pull in their arms. The resulting black hole can be spinning very rapidly at speeds approaching the speed of light at the event horizon. A spinning black hole is described by the Kerr solution, named after the New Zealand mathematician Roy Kerr, who found the solution in 1963. Kerr black holes have a very different interior structure than Schwarzschild black holes, and falling into one would be a very different experience. The most striking feature of a Kerr black hole is that it has two event horizons, an outer one and an inner one, known as the Cauchy horizon. Between the two horizons, the character of the singularity changes, and the singularity itself is not a point, it's a ring-shaped singularity that lies in the equatorial plane of the black hole, spinning at enormous speeds. The existence of the ring singularity opens up tantalizing, if speculative, possibilities. In the mathematical solution, it is possible to pass through the ring without hitting the singularity, emerging into a different region of space-time. Some interpretations suggest that this other region might be another universe, or a different part of our own universe. The Kerr solution, taken at face value, describes a geometry that connects different regions of space-time through the interior of the black hole, a kind of wormhole. The inner Cauchy horizon is believed to be unstable to perturbations, meaning that any small amount of infalling matter or radiation would cause it to collapse into a singularity, closing off the passageway and preventing anyone from passing through. This is sometimes called the mass inflation instability, and it suggests that the smooth, traversable interior of the mathematical Kerr solution is an idealization that doesn't survive contact with the messy reality of actual physics. Still, the structure of the Kerr black hole is fascinating, and it hints at the deep connections between gravity, space-time, and the topology of the universe that a full theory of quantum gravity might reveal. There's another aspect of spinning black holes that's worth mentioning. The spin of a Kerr black hole creates a region outside the event horizon called the ergosphere. Within the ergosphere, space-time itself is dragged along by the black hole's rotation, a phenomenon called frame dragging. Objects within the ergosphere cannot remain stationary. They are dragged along in the direction of the black hole's rotation, regardless of how hard they try to resist, but they can still escape. The ergosphere is outside the event horizon, so escape is possible, you just can't stand still. The ergosphere makes possible a remarkable energy extraction process called the Penrose process, proposed by Roger Penrose in 1969. In the Penrose process, a particle enters the ergosphere and splits into two pieces. One piece falls into the black hole, and the other escapes, carrying more energy than the original particle had. The extra energy comes from the rotational energy of the black hole, which is reduced by the process. In effect, you can extract energy from a spinning black hole by throwing things into its ergosphere and catching the pieces that come back out. The maximum efficiency of the Penrose process is about 29%, meaning up to 29% of the rest mass energy of the infalling object can be extracted. This is far more efficient than nuclear fission, which extracts less than 1%, or nuclear fusion, which extracts less than 1%, or nuclear fusion, which extracts less than 1%. And in the idealized case of a maximally spinning black hole, the efficiency of the accretion disk can reach 42%, making black hole accretion the most efficient known process for converting mass into energy. Let's shift our attention to another question, a question that might be forming in your mind as you lie there in the dark, imagining this impossible journey. The question is, could we ever observe what happens inside a black hole? Could we ever know what's in there? The answer, according to our current understanding of physics, is no. The event horizon is an absolute boundary. Nothing from inside can reach the outside. No signal, no message, no particle, no photon can escape. Whatever happens inside a black hole is forever hidden from external observation. But there are subtle ways in which the interior of a black hole might leave traces on the outside. Gravitational waves, for instance, are ripples in space-time produced by accelerating masses. When two black holes merge, they produce a burst of gravitational waves that carries information about the mass, spin, and orbital dynamics of the system. The final moments of the merger, when the two event horizons fuse into one, are encoded in the gravitational wave signal, a chirp of increasing frequency and amplitude that has been detected multiple times by the LIGO and Virgo observatories. These signals don't tell us what's inside the black holes, but they tell us about the geometry of space-time near the event horizons, providing indirect constraints on the interior structure. Hawking radiation, if it could be detected, might also carry information about the interior, though this remains deeply controversial. The radiation is so faint for astrophysical black holes that it is completely undetectable with any foreseeable technology. A stellar mass black hole emits Hawking radiation at a temperature of about 60 billionths of a Kelvin, far colder than the cosmic microwave background, which has a temperature of about 2.7 Kelvin. The radiation is utterly overwhelmed by the ambient temperature of the universe. Only in the very far future, when the universe has expanded and cooled to temperatures below the Hawking temperature, will black hole evaporation become the dominant process, and that won't happen for timescales so long that they make the current age of the universe look like an instant. Let's think about time for a moment. Let's think about how much time a black hole has. The evaporation time for a black hole due to Hawking radiation is proportional to the cube of the black hole's mass. For a stellar mass black hole of about 10 solar masses, the evaporation time is about 10 to the 68th years. That's a 1 followed by 68 zeros. For comparison, the current age of the universe is about 1.38 times 10 to the 10th years, a 1 followed by 10 zeros. The evaporation time is roughly 10 to the 58th times the current age of the universe. It's a number so large that it's essentially meaningless in any practical sense. For our supermassive black hole with 10 million solar masses, the evaporation time is even longer, about 10 to the 89th years. And for the largest known black holes with masses of tens of billions of solar masses, the evaporation time approaches 10 to the 100th years. A googol years. These are timescales that dwarf anything else in the physical universe. The stars will have all burned out, the galaxies will have dissolved, the protons and neutrons that make up ordinary matter may have decayed. And the black holes will still be there, patiently radiating so slowly that a single photon of Hawking radiation might be emitted once every trillion years. But eventually, even the black holes will die. They will shrink slowly, imperceptibly over these impossible timescales, growing hotter as they shrink, radiating more intensely, accelerating their own demise. In the final moments, the evaporation becomes explosive. The last fraction of a second of a black hole's life releases a burst of energy, a final flash of Hawking radiation, as the remaining mass is converted entirely to energy. And then the black hole is gone. The singularity, the event horizon, the warped space-time all vanish, leaving behind only the faint, dispersing remnant of the final burst of radiation. And the information about everything that ever fell into the black hole, every star, every planet, every photon, every bit of quantum information. Either it was encoded in the Hawking radiation all along, carried out in subtle correlations that only become apparent when the entire history of the radiation is analyzed, or it was stored in a remnant, or it was lost. We don't know. The resolution of the information paradox remains one of the great unsolved problems. Let's come back to the experience. Let's come back to the human scale of this journey, because behind all the equations and theories and abstract concepts, there's something deeply moving about the idea of falling into a black hole. It's a journey into the unknown in the most literal sense possible. A journey beyond the reach of physics, beyond the reach of knowledge, beyond the reach of communication. It's the ultimate one-way trip, and it raises questions that are not just scientific, but philosophical. What does it mean to cross a boundary that you can never recross? What does it mean to enter a region from which no information can escape? Is the person inside the black hole still part of our universe? Are they still real, in any meaningful sense, if nothing they do or say or think can ever affect the outside world again? These questions touch on the deepest issues in the philosophy of physics, the nature of reality. The meaning of observation, the relationship between information and existence, they are questions that we cannot answer with equations alone. They require us to think about what we mean by existence, by knowledge, by the self, and they remind us that the universe is not just a collection of objects and forces. It is a collection of questions, many of which remain open, many of which may remain open forever. Let's think about what the journey into a black hole tells us about the nature of space and time, because that perhaps is the most profound lesson of all in everyday life. We experience space and time as separate, distinct things. Space is the arena in which things exist. Time is the clock that measures change. Space has 3 dimensions: left, right, forward, backward, up, down. Time has 1, past to future. Space is something we can move through freely in any direction. Time is something we move through in only one direction, forward at a fixed rate, but general relativity tells us that this separation is an illusion. Space and time are not separate. They are aspects of a single 4-dimensional entity called space-time, and space-time is not a fixed, rigid stage on which events play out. It is dynamic. It curves and warps and ripples in response to the matter and energy within it. The curvature of space-time is gravity. And the more extreme the curvature, the more profoundly space and time are altered. Inside a black hole, this alteration reaches its most extreme form. The roles of space and time are, in a sense, exchanged. The direction toward the singularity, which outside the horizon is a direction in space, becomes inside the horizon a direction in time. And the direction of time, which outside the horizon flows from past to future, becomes inside the horizon a direction in space. This is not a metaphor, it's a precise mathematical statement about the structure of the Schwarzschild metric, the equation that describes the geometry of space-time around a non-rotating black hole. Inside the event horizon, the time coordinate and the radial coordinate exchange their mathematical roles. The singularity is not a place, it's a time. And falling toward the singularity is not traveling through space, it's traveling through time, the future. This role reversal is one of the most mind-bending aspects of black hole physics, and it's worth letting it sink in. We are used to thinking of space and time as fundamentally different. Space is something we navigate, time is something that happens to us. But near and inside a black hole, this distinction breaks down. Space-time is one thing, and its components can be shuffled and rearranged by extreme curvature. The universe is stranger and more flexible than our everyday intuitions suggest. Let's talk about something else that happens near black holes, something that Einstein predicted but that wasn't confirmed until very recently: the phenomenon of gravitational wave. When two black holes orbit each other, they lose energy by emitting gravitational waves, ripples in the fabric of space-time that propagate outward at the speed of light. As they lose energy, the black holes spiral closer together, orbiting faster and faster, emitting stronger and stronger gravitational waves. The process accelerates. The black holes approaching each other at increasing speed, the gravitational waves growing in frequency and amplitude, creating a characteristic signal called a chirp. In the final fraction of a second, the two black holes merge, their event horizons fusing into a single larger event horizon, and a final burst of gravitational waves is emitted as the merged black hole settles into a stable state. The energy released in a black hole merger is astounding. In the first detection by LIGO, the merger of two black holes of about 30 solar masses each released about 3 solar masses worth of energy in the form of gravitational waves in less than a second. That's more energy than all the stars in the observable universe were emitting in light during that same second. For a brief moment, the gravitational wave luminosity of the merger exceeded the electromagnetic luminosity of the entire observable universe. And yet, by the time the waves reached Earth, they had spread out over such an enormous volume of space that the signal was almost unimaginably faint, stretching and compressing the LIGO detectors by about 1,000th the diameter of a proton. The detection of gravitational waves was one of the greatest scientific achievements of the 21st century. It confirmed a prediction that Einstein had made 100 years earlier. It opened a new window on the universe, allowing us to observe phenomena that are invisible to electromagnetic radiation, and it gave us direct evidence of the merger of black holes, objects that are by definition invisible, by detecting the ripples they create in the fabric of space-time itself. Since the first detection in 2015, LIGO and Virgo have detected dozens of gravitational wave events from merging black holes, merging neutron stars, and mixed mergers of a black hole and a neutron star. Each detection provides information about the masses, spins, and distances of the merging objects, building up a census of the black hole population in the universe. The results have been surprising. Many of the black holes detected by LIGO are more massive than expected, with masses of 30, 40, even 85 solar masses, challenging our understanding of how black holes form from stellar collapse. Some of these massive black holes may have formed from the merger of smaller black holes, or from the collapse of unusually massive stars, or through processes that we haven't yet identified, the future of gravitational wave astronomy is extraordinarily promising. The next generation of gravitational wave detectors, including the Einstein telescope in Europe and Cosmic Explorer in the United States, will be 10 times more sensitive than LIGO, allowing them to detect mergers at much greater distances and with much greater precision. The space-based detector LISA, planned for launch in the 2030s, will be sensitive to lower frequency gravitational waves, allowing it to detect the mergers of supermassive black holes, the coalescence of the enormous black holes at the centers of galaxies, events that release more energy than almost anything else in the universe. These observations will tell us about the population of black holes across cosmic time, the history of galaxy mergers, the properties of matter under extreme conditions, and perhaps, if we're lucky, something about the nature of gravity itself. They may even reveal deviations from general relativity, hints that Einstein's theory, for all its triumphs, is not the final word on gravity. Every theory in physics is provisional. Every theory is an approximation, valid within a certain domain of applicability. And every theory is eventually superseded by something deeper, something more complete, something that explains what the previous theory could not. General relativity will be no exception. Somewhere in the data from gravitational wave detectors, or from observations of black holes, or from some experiment we haven't yet imagined, there may be a clue, a hint. A thread that, when pulled, unravels the current framework and reveals something new. Let's return one last time to the experience of falling into the black hole. Not to the physics, but to the feeling, the human dimension of this impossible journey. Imagine the loneliness. You are falling into a region of space-time from which you can never return, never communicate, never be heard. The universe you left behind continues without you. Stars are born and die. Civilizations rise and fall. Billions of years pass, and you are inside the black hole, isolated, cut off, falling toward a singularity that you cannot understand and cannot avoid. You are the loneliest being that could ever exist, separated from the rest of reality by the most absolute barrier in physics. And yet, the view is extraordinary. The entire observable universe, compressed by gravitational lensing into a brilliant circle of light above you, a window onto everything that exists, everything that has ever existed, squeezed into a disk of blue-shifted starlight. You can see it all, or at least a version of it, distorted and shifted, but real. The cosmos is still there, still vast, still beautiful. Still going on without you. And you are watching it from inside a black hole, seeing it from a perspective that no other being in the universe will ever share. There's a poetry in this, a terrible, beautiful poetry. The idea that the most extreme journey possible, the descent into the deepest gravitational well in the universe, also provides the most extreme perspective on the universe itself. From inside a black hole, you see everything and can tell no one. You understand what is happening to you, at least in broad terms, and you're powerless to change it. You are a witness to the ultimate expression of gravity, the force that shapes the cosmos, the force that holds galaxies together and pulls stars into collapse and bends light and warps time. And you are subject to it, completely, utterly, irrevocably subject to it. Let's step back now. Let's pull away from the black hole, away from the singularity, away from the event horizon, and float in the quiet darkness of intergalactic space. The black hole is behind us, or rather, the imagined experience of it is behind us. We're safe. We were always safe. This was a thought experiment, a journey of the mind, a way of exploring the most extreme physics in the universe through the lens of human experience. But the black holes are real. They're out there, tens of millions of stellar mass black holes in our galaxy alone, the collapsed remnants of massive stars wandering through the interstellar medium, invisible and silent. Supermassive black holes at the centers of most, perhaps all, large galaxies containing millions or billions of solar masses, shaping the evolution of their host galaxies through their gravity and their occasional episodes of violent feeding. And perhaps primordial black holes, formed in the first moments after the Big Bang, from density fluctuations in the hot, dense plasma of the infant universe, ranging in size from microscopic to enormous. Black holes are not rare, they are not exotic, they are a fundamental feature of the universe, as common and as important as stars and galaxies. They are the endpoints of stellar evolution, the engines of active galactic nuclei, the sources of the most powerful gravitational wave signals, and the laboratories in which the most extreme physics in the universe plays out. They are where general relativity meets its limits, where quantum mechanics meets its limits, where our understanding of reality meets its limits. They are, in a very real sense, the frontiers of physics, and they are beautiful, not in the conventional sense, not in the way that a sunset or a flower is beautiful, but in the way that a deep mathematical truth is beautiful. The Schwarzschild solution, the Kerr solution, the Penrose diagrams that map the causal structure of black hole spacetimes, these are some of the most elegant and profound constructions in all of physics. They reveal a universe that is far stranger, far more creative, far more surprising than anything we could have imagined. A universe where space and time are woven together and can be warped and torn. A universe where the geometry of space-time is determined by its contents, and the contents are determined by the geometry in an endless dynamic feedback loop. A universe where the simple, intuitive notions of distance, duration, direction, and location break down under extreme conditions, replaced by something deeper, something more fundamental, something that we are still struggling to understand. Let's think about what we've learned on this journey, not just the facts, but the lessons. We've learned that the event horizon is not a wall. It's a boundary defined by the global structure of space-time, undetectable to a local observer, yet absolutely final. We've learned that crossing it feels like nothing, that the most dramatic boundary in the universe is the most subtle. We've learned that inside the black hole, the singularity is not a place, but a time, a future that cannot be avoided. We've learned that tidal forces, the manifestation of space-time curvature, will eventually destroy anything that falls in, but that for a supermassive black hole, the destruction is delayed, giving the infalling observer hours or even days of continued existence. We've learned that the view from inside a black hole includes the entire outside universe, compressed into a brilliant ring of light, visible but unreachable. We've learned about the information paradox and how the existence of black holes forces a confrontation between our two most fundamental theories of physics. We've learned about Hawking radiation and the slow, patient death of black holes over timescales that dwarf the current age of the universe. We've learned about gravitational waves and how the merger of black holes produces signals that can be detected across billions of light years, opening a new window on the universe. And we've learned, perhaps most importantly, that the universe contains phenomena that push our understanding to its absolute limits. That there are places in the cosmos where our best theories fail, where our deepest intuitions mislead us, where the nature of reality is so different from our everyday experience that it can only be grasped through mathematics, imagination, and a willingness to accept that the universe is under no obligation to make sense to us. That's a humbling lesson. And it's a thrilling one, because it means that there is more to discover, more to understand, more to explore. The singularity at the center of a black hole is not just the end of a journey, it's the beginning of a question a question about the ultimate nature of space and time, matter and energy, information and existence. A question that may take decades or centuries to answer. A question that will require new theories, new experiments, new ideas that no one has yet imagined. And somewhere in the universe, right now, at this very moment, matter is falling into a black hole. A star, torn apart by tidal forces, is being stretched into a long, thin stream of gas that spirals around the event horizon, heating up, radiating, blazing with light, before crossing the threshold and vanishing from the observable universe forever. Somewhere, two black holes are spiraling toward each other, locked in a gravitational embrace that will end in a collision, a merger, a burst of gravitational waves that will ripple across the cosmos at the speed of light, carrying information about the most violent event in the universe. Somewhere, a supermassive black hole at the center of a distant galaxy is quietly feeding, accreting gas from its surroundings, growing slowly, patiently, as it has for billions of years. And somewhere, a photon of Hawking radiation is being emitted from the event horizon of a small, isolated black hole, drifting through the void of intergalactic space, carrying a tiny fraction of the black hole's mass energy, contributing to the slow, inexorable evaporation that will, over timescales of 10 to the 68th years, reduce the black hole to nothing. A photon that carries perhaps a tiny fragment of the information about everything that ever fell in, encoded in subtle quantum correlations that we do not yet know how to read. The universe is full of black holes, and each one is a story of stellar death and gravitational collapse, a story of extreme physics and broken symmetries, a story of information and its fate, a story of the limits of knowledge and the boundaries of the knowable. We've told one of those stories tonight, the story of a fall, a slow, gentle, terrifying, beautiful fall into the darkest, deepest, most extreme place in the universe, a place where time becomes space and space becomes time, a place where the curvature of reality becomes infinite, a place where our best theories break down and the unknown begins. Let your mind settle now. Let the images of warped starfields and blazing accretion disks and infinite darkness fade into the background. Let the numbers, the millions of solar masses and the billions of kilometers and the impossible timescales, let them all dissolve into a quiet sense of wonder. The black hole is there. It will always be there, or at least for a time so long that it might as well be always. And we are here, brief, fragile, aware, looking up at the sky or imagining it and wondering what lies at the heart of the darkest objects in the cosmos. The answer for now is that we don't know. And that's okay. Not knowing is not a failure. It's an invitation. An invitation to keep looking, keep thinking, keep asking. The universe has been hiding its deepest secrets inside black holes for billions of years. It can keep them a little longer. We're patient, we're curious, and we have time. Not as much time as a black hole, but enough. Let your breathing slow. Let the tension leave your body. The journey is over. The black hole is far away. A theoretical construct, a thought experiment, a story told in the dark to help you understand the universe and your place in it. You are not falling. You are resting. You are safe. You are on the surface of a small blue rocky planet orbiting an ordinary star in the suburbs of an ordinary galaxy. The ground beneath you is solid. The air around you is still, and the stars above you, if you could see them, are shining steadily, as they have for billions of years. Some of those stars will, one day, collapse into black holes. Some of them already have. The galaxy is full of them, invisible sentinels, dark remnants of stars that burned and died long before the Earth was born. They are part of the landscape of the cosmos, as natural and as necessary as the stars themselves. Without the deaths of massive stars, there would be no heavy elements, no rocky planets, no life. Without the black holes, there would be no gravitational waves, no quasars, no active galactic nuclei, no mechanism for regulating star formation in galaxies. Black holes are not just destroyers, they are creators. They are part of the cycle of cosmic renewal, the endless process of birth, death, and rebirth that has been driving the evolution of the universe for 13.8 billion years, and they are laboratories. Places where the most extreme physics plays out, where the most fundamental questions about the nature of reality are encoded in the geometry of space-time. Every black hole is a puzzle. Every black hole is a clue, and every time we observe one, study one, detect the gravitational waves from one, we learn something new. Something that brings us a little closer to understanding the universe we live in, something that pushes the boundary of knowledge a little farther out, into the unknown. The unknown, that's where we've been tonight. Not just the inside of a black hole, but the inside of the unknown itself. The place where our theories end and our questions begin. The place where the universe keeps its deepest secrets, locked behind event horizons and encoded in singularities, waiting for someone to find the key. We don't have the key yet, but we're looking, and the looking itself is a kind of journey. A journey without a destination, without a final answer, without an end. A journey that is, in its own way, as infinite and as beautiful as the universe itself. Sleep now. Let the darkness of the room become the darkness of space. Let the silence become the silence between the stars. Let the heaviness of your body become the gentle pull of gravity, the same force that shapes the cosmos, the same force that bends light and warps time and creates the most extreme objects in the universe. You are made of the same stuff as the stars, the same atoms, the same forces, the same physics. The gravity that creates a black hole is the same gravity that holds you to the Earth, that keeps the moon in its orbit, that binds the galaxy together. You are part of this story. You are part of the universe's long, slow, beautiful exploration of its own possibilities, and the black holes are part of it too, dark, patient, mysterious, holding their secrets behind horizons of no return, waiting for the universe to cool, to age, to evolve, waiting with infinite patience for the long, slow death that Hawking predicted. The evaporation that will take longer than any other process in the cosmos. Waiting for the end, or for a new beginning, whatever lies beyond the singularity, beyond our theories, beyond our understanding. The stars are still shining, the galaxies are still spinning, the gravitational waves are still rippling through space-time, carrying messages from colliding black holes billions of light years away. And you are here, breathing, resting, existing on a tiny planet in a vast cosmos, aware of it all, or at least of a tiny fraction of it all, and that fraction is enough. More than enough. It's everything. Good night, sleep well, and dream. If you dream at all of the quiet darkness at the center of everything, it's not as frightening as it sounds. It's just the universe, doing what it does, being strange, being beautiful, being more than we can comprehend, but no more than we can wonder about. The stars will be there in the morning. The black holes will be there too, hidden in the dark, patient and eternal, and the questions will still be waiting. They always are. Thank you for traveling with us tonight on Neptune Files.